Rethinking Eye-Blink. This work is by Youngjun Cho from University College London. In this work, we are concerned with mental workload assessment through physiological computing. Mental workload that can be defined as the cognitive demand of tasks has been extensively explored across fields including human-computer interaction. Mental workload assessment is obviously one of the important tasks in usability and accessibility evaluation. With self-report questionnaires such as NASA TRX, physiological measurements and their metrics have often been used for mental workload assessment. And here, there could be two major types of studies to be considered. The first type is to investigate the causal effects of cognitive load factors on physiological metrics, and the other type aims to estimate mental workload parameters such as expected task difficulty through supervised machine learning of physiological measures. Our main consideration is spontaneous eye blink responses to task difficulty. This is because existing eye blink measures appear to play a very minor role in the first study type and much less explored in the second type as well, even though they can be easily measured using a webcam in our daily life, not requiring a specialized physiological sensing device. Earlier studies have explored this with two key standard metrics, blink rate and blink duration. There have been inconsistent findings on the relationship between blink rate and task difficulty levels. Also, the metrics are shown to be sensitive to perceptual load such as visual stimuli rather than task difficulty, and they are prone to their interaction effects. So, this has been the main challenge in bringing blink measures to the mental workload estimation task. Here, we wanted to revisit and address this problem, proposing Rethinking Eye-Blink, which is a novel framework for automatic task difficulty estimation through physiological representation of spontaneous blinking. The framework consists of three stages. The first two are for the physiological representation to replace existing metrics and to improve their sensitivity to task difficulty. In detail, the first stage is to extract raw blink time series through face landmark detection. And in the second stage, our blink spectrogram generator converts the time series to time frequency spectrograms. On the right side is a video to show blink spectrogram generated in real time. Finally, the last stage is feature learning with two-dimensional long short-term memory neural networks to achieve a strong nonlinear mapping from blink spectrograms to difficulty-related parameters. With the proposed framework, we conducted the two aforementioned studies. In the first study, where we used a mental arithmetic task, one of the most standard ones in exploring task difficulty effects in many fields, we revisited the sensitivity of the standard blink metrics to understand the extent to which a blink representation improves its sensitivity. Here, we used blinker entropy to quantify our blink spectrogram. And the result has confirmed that the representation can improve blink measure sensitivity and highlighted the importance of exploring time frequency representation of eye blink when capturing its response to task difficulty. From the task difficulty estimation study, using leave one subject out cross-validation to test the generalizability, our method produced state-of-the-art accuracies, outperforming the other baseline approaches that used the handy-engineered blink metrics. This comparison result confirms that the sensitivity gain and improved performance are indeed from the more powerful representation rather than the more powerful machine learning classifier. Lastly, we highlight some benefit from machine learning. Pre-trained models in lab settings are scalable in real-life situations where datasets grow. Having said that, here we consider some of the real-world applications like usability evaluation for websites and accessibility monitoring in VR applications. That's the end of my presentation. Please check out the paper for more details, and the source code is also available on GitHub. Thanks for listening.